All right, we're going to take a look at finding the domain of a rational function. It says to find the domain of each rational function, and when we're looking for domain, the thing to remember is it's asking for us to determine which x values would actually create the graph, or in other words, which would cause there to be a picture on a coordinate plane. And that really translates into which x's could we put in that wouldn't break any real math rules, meaning this. If I looking at this function right here, I see that if I put in a value of x is equal to 1, if I input a value of x is 1, then what I would have is this, 1 minus 2 over 1 minus 1, and that would give me a negative 1 over 0. And we know that this is no man's land. This right here, it means that there is no value at at positive 1. There's no value because we get the result of undefined. We get undefined. In other words, we get a 0 on the bottom of the fraction. What that just means is that when I look at a picture of this graph, I actually have a vertical asymptote at x equals 1. And so there is no graph there. So that's what we're really saying. When we're looking for the domain of a function, then we're looking for where the graph appears on the coordinate plane when we graph it, but also that relates to and connects to what values of x would cause there to be some kind of broken math rule. Well, in this case, the broken math rule would mean that the value at 1 is undefined. We don't have even a definition for when we put in an x of 1. It's undefined. There is no picture there. So, how do we do this? How do we always know what values we would have to toss out of our possible x values? Well, we look at the bottom of the fraction. We look at the denominator. And we take a look and say, hey, what would cause the denominator to be 0? Well, here's what we can do. We can just set the denominator equal to 0. If what would cause the denominator to be 0 is found by making the denominator 0, then I've solved the problem. So let's go ahead and find out what would, we already know the answer, but let's do it algebraically instead of guess and check. If I take the denominator and make it 0, then I find out what would not work in this function. Okay? So x equals 1 is not part of the domain. So here's how I would write that. I would say that then x can't be, okay, x can't be, oops, let me do it this way, x cannot be a 1. So when I'm writing the domain, here's what I'm going to write. I'm going to say negative infinity to 1, not including 1, union 1 to infinity. In other words, I'm going to bounce right around 1, and that's my domain. Any value of x will work except for the value of 1, because there's no picture there. And if you wanted to put this in your graphing calculator, you would see, indeed, there is no value, there's no picture at x is 1. Okay, let's take a look at this next one here. So what we said before was if I want to know what would cause the denominator to be 0, which is that's the values that I would have to toss, that I would have to throw out, then I'm going to set the denominator equal to 0. So then I get x squared is equal to 9, and I get x is plus or minus 3. So x cannot be a 3, and it cannot be a negative 3. That means I have two vertical asymptotes at this place. Okay, now, these are all presuming that I've already factored the numerator, okay, and that I've already canceled anything in common. If I have something in common that can cancel, then that's not one of the asymptotes. So we'll look at that in a little bit. But for these problems right here, nothing cancels above and below, and so therefore I know that whatever's remaining on the denominator is what I'm going to set equal to 0, and those are basically the places where there's no man's land. So how would I write the domain for this one? I would do this. I would say the domain for this one is negative infinity to negative 3, not including negative 3, union, negative 3 to 3, union, and yes, we can have several of these, 3 to infinity. In other words, I'm just going right around the negative 3 and the 3. And I can use anything else. In fact, if you want to see it on a number line, this might be helpful. Okay, here's the actual, here's the actual coordinate plane, and it means that there'll be values up and down from here. There'll be values up and down from here, and values up and down from here. In other words, the graph will show values everywhere except these two places here, except there and there. And at those places, we'll have a vertical asymptote. So here we'll have values, here we'll have values, and here we'll have values. Somewhere in here, anywhere in here, but we won't have any at the negative 3 and the 3. Okie doke. Hope this was helpful. Thanks for